All right, so this is going to be our first video on indeterminate forms and L'Hopital's rule. We're going to be focusing on 0 over 0 and infinity over infinity in this video. So traditionally back in your first calculus course, if you had a limit for f of x function as x goes to a and another limit for g of x, then if you were to plug these into the limit of f of x over g of x, you would just calculate this as L1 over L2. However, there is a special case when you get 0 over 0, and this is going to be our first indeterminate form. And we call it indeterminate because we don't really know which one is going to 0 faster without some further analysis. So maybe in your Cal 1 course, you would have looked at a limit like this. You could factor the top, factor the bottom. You end up having a common factor. There's a whole or removable discontinuity at x equals 2. That's what's causing that 0 over 0. But then once you simplify this, you can plug in. You might have also seen sine of x over x. If you plug in 0, you get 0 over 0 again. But we can use what's called squeeze theorem and look at that graphically to see what's going on here. Okay, and here's a little bit more of that in detail if you would like to look at those, okay? However, we're going to look at a different technique called L'Hopital's rule, and this is in the 0 over 0 case. So what's really important with L'Hopital's rule is we're not doing quotient rule, okay? What it's saying is the ratio of f of x over g of x must have a similar behavior or ratio between its derivatives. So you're going to take the derivative of the top, the derivative of the bottom, and that ratio should stay consistent when we're looking at the limit as x goes to a. Okay. This is also going to hold true if we're considering one-sided limits as well. So if a is going to positive or negative infinity, this is also going to be something that holds true. So if you're looking at two different exponential decay functions, okay, they're both going to 0 as x goes to infinity. This is also going to be true for those. So let's look at a couple examples. So the first thing you're always going to want to do is still plug in your a term. So on this first one, a equals 0. If I plug that in, I get 1 minus the cosine of 0 over 0. That gives me 0, because 1 minus 1 gives me 0 over 0. We call this now an indeterminate form. So instead, I can use L'Hopital's rule and take the derivative of the top, 0, and then let's see, sine, cosine, negative cosine. Negative cosine's derivative is positive sine. And then the derivative of the bottom is 1. I can plug in, I get 0 plus sine of 0 over 1. 0 plus 0 over 1 is 0, and so that's going to be my answer. All right, let's look at B. As x goes to infinity, let's think about what's going on here. So I'm going to plug in infinity. I know that that's not always the best, like, notation-wise. 1 over infinity gets really, 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 really small. It's like it approaches 0. Again, I'm going to get 1 minus 1 in the top, 0 over 0. All right, so let's go ahead and use L'Hopital's rule in order to evaluate this. The derivative of the top is e to that function times the derivative of that function, negative 1 over x squared, minus 0, all over, and then the derivative of the bottom. So the derivative of 1 over x is negative 1 over x squared. Now this minus 0 doesn't really matter. I have a same factor in the top and the bottom with a multiplication here. So these two factors do cancel. I'm now just looking at plugging in infinity here, or e to the 0, which is 1. All right, we can also use L'Hopital's rule when we get infinity over infinity. Again, we're not quite sure we need further evaluation to know that we are, which one is going to infinity faster. If the top's going to infinity faster, the whole thing goes to infinity. If the bottom's going to infinity faster, the whole thing's going to zero. But it is an indeterminate form just as infinity over infinity. So we don't divide them and get one, okay? Infinity over infinity is just okay, these are both approaching infinity without bounds. So I can use L'Hopital's rule here in order to evaluate this limit. All right, so let's go ahead and look at this first one. If I were to plug in infinity, I would get infinity over infinity. So L'Hopital's rule says I can take the limit as x goes to infinity. The derivative of the top is 3. The derivative of the bottom is 2. And so I get 3 halves. Now, if you think back to when you talked about rational functions in your pre-cal class, you might have looked at the first terms here and said, oh, this would have a horizontal asymptote or end behavior at the ratio of the coefficients, because x to the power of 1, x to the power of 1, you would have gotten this, and limits as x goes to infinity are the same thing as horizontal asymptotes. All right, let's think about what's going on. This limit as x goes to 0 from the right. Well, natural log is going to go to negative infinity, and so is cotangent. Let's think about cotangent's graph. Oh, it's actually going to go to positive infinity. Still, okay, and we don't just say oh, it's -1. That's not what we do here, okay? We say oh, this is indeterminate. And we're going to then take the derivative of the top, 1 over x. The derivative of the bottom, the derivative of cotangent is negative cosecant squared. All right, let's do a little bit of some flipping around here. So I have 1 over x times, okay, this is negative cosecant over 1. So if I multiply by the reciprocal of that, now cosecant is 1 over sine, so this is going to end up being, let me move this up just a smidge, give me a little more room. The limit as x goes to 0 from the right of 1 over x times negative sine squared x over 1. All right, well, I might have to use L'Hopital another time here, because if I plug in 0, I'm going to end up getting 0 over 0 on this one. So I'm going to use L'Hopital's rule again and take the limit as x goes to 0 from the right. All right, let's take the derivative here. I got to do some chain rule. So -2 sine x, and then times the derivative of the inside, so times cosine x, and then the derivative of the bottom would be 1. All right, now when I plug in 0, I get 0 over 1, which gives me 0. All right, let's look at one more example. Now, sometimes when we learn something brand new, we want to use it all the time, okay? And I want to show us in this example that you aren't always just going to use L'Hopital's rule. The first thing you should always do is plug in. So if I were to plug in, I would get 1 squared 1 plus 5 over 3 times 1, 3 plus 4. So 6/7. And that is my answer. This function, if you were to graph it, get really, really close to 1 on your x values. Your y values are going to approach 6 over 7. Now let's just say we try to use L'Hopital's rule here. All right, when I plug in 1, see, I get 2/3. That's not true. That's not equal to 6/7. So L'Hopital's rule only works if you get one of these indeterminate forms, and it allows you to evaluate the rates of change, the ratios of the rates of change, because your function on the top is going to 0, your function on the bottom is going to 0, or infinity over infinity, and we need to know which one is going to those faster. And we look at that by using rates of change, which is also derivatives.